Hello everyone and welcome to my presentation where I will be talking about selecting features from time series using attention-based recurrent neural networks. Here is the agenda. I will briefly talk about our goals and motivation, introduce you to recurrent neural networks, explain our proposed solutions, present the results and draw some conclusions. So nowadays we collect more and more data, and this often leads to noisy or low quality datasets. And this phenomenon is called the curse of dimensionality, where high-dimensional data becomes sparse and dissimilar in many ways. It makes it harder to obtain sound and reliable results, and this is why we want to filter out the redundant features presented on the left plot, which are strongly correlated with each other, as well as the irrelevant features presented on the right plot, which do not bring any useful information regarding the separation of two classes. In our work, we wanted to propose a feature selection algorithm that could be incorporated into any model and is fully customizable. Also, we verify whether this proposed algorithm extracts meaningful features, and we do that by classifying dimensionally reduced data and compare it to the model that was trained on a full set of features. We also verify whether the attention model that is attached to the baseline model can improve its classification performance. And finally, we verify whether our algorithm is capable of outperforming some state-of-the-art methods. We have chosen the principal component analysis as the feature extraction method and mutual information as the feature selection method. In order to fully test the performance of the algorithms, we use a wide variety of different datasets, and the first of them is the UVanemo dataset, which is a database of videos where people are either smile spontaneously or pause their smile. It consists of 1040 smile videos and it is more or less balanced. The second set of datasets are hyperspectral images, namely Pave University and Salinas Valley. Pave University contains 103 hyperspectral bands with 9 classes, and Salinas Valley contains 204 hyperspectral bands with 16 classes. So there's definitely a room for improvement in terms of dimensionality reduction. The last dataset that we use is the heartbeat electrocardiogram sequences dataset, and it consists of 5000 time series samples, where each of them has 140 time steps. This is a binary dataset where we distinguish between healthy and ill patients. RNNs are a class of neural networks that allow previous outputs to be used as inputs while having hidden states, and it makes them a perfect candidate to process time series datasets. One of their advantages is that they can process input of any length, and also that they take into account a historical information that was previously in the sequence. Here we can see the baseline model, and it is a simple two-layered LSTM neural network followed by 3 fully connected layers with their respective activation functions. And it is important to notice that it accepts only the last time step of the LSTM network. And here we can see the method that we propose, which is the attention module as well as the attention classifier. So the attention module accepts all of the time steps from the LSTM neural network and returns their relevance. Such vector is then used to weigh those time steps, and such weighted vector is then fed to the attention classifier, which returns the prediction. Its prediction is averaged with the standard classifier that accepts only the last time step of the LSTM network, which we saw previously on the baseline model. So we have kept the original part of the model and incorporated the attention part on the left side. Here are the quantitative results. We have 4 different metrics: overall accuracy, balance accuracy, F-run score, and specificity. And we have chosen to extract from 2 to 25 features, as well as train the models on full set of features. The main takeaway is that the model enhanced with the attention model outperformed the baseline in most scenarios. Also, it is important to notice that PCA outperformed other methods in hyperspectral data by quite a margin, but failed to capture important information in the UVANEMO dataset, where it scored very poorly, giving only slightly better results than random guessing. Also, we were happy to see that the attention algorithm was able to keep up or even be better in some cases than the other feature selection algorithm that we compared to, namely mutual information. Here is the example of frames where our attention-based model correctly classified them as spontaneous and deliberate, whereas the mutual information algorithm failed to do so. We can see that the spontaneous sequence might be hard to spot because the lady is smiling very slightly. However, the deliberate sequence is easy to spot even for humans. To understand the behavior of feature selection methods, we have visualized their heatmaps. These are the two bars on the bottom of the plot, and compared it with average pixels value for all of the classes. So the attention indicated the most important features between 20 and 40 for the Pavia University dataset, discarding almost all of the rest. However, the mutual information also indicated the very end of the spectrum as meaningful, and we can see that we can distinguish the curves of the classes very well in these points. As for the Selena dataset, the attention once again indicated the very end of the very beginning of the spectrum as important, discarding features as we go on further into the spectrum, and we can see that indeed the differences between classes start to diminish as we go on. This is not the case for the mutual information, where it indicated a lot of points where features might be important. And lastly, for the heartbeat electrocardiogram sequence dataset, once again attention indicated the beginning of the spectrum as important, and the mutual information also indicated some spots at the end of the spectrum as important. And indeed we can see the differences in the curves at those points. To prove a winner, we have ranked all of the algorithms, and we can see that the baseline model enhanced with the attention was able to win in terms of overall accuracy. However, in terms of balance accuracy, the PCA algorithm was able to be the best, and this might be due to its exceptional performance in hyperspectral datasets. We are also happy to see that attention was ranked better in terms of balance accuracy than the mutual information. And also the main takeaway is that more features does not necessarily mean better performance. We can see that, for example, for PCA with only 10 features, the rank is higher than, for example, for PCA with 25 features. Summing up, we have proposed the attention-based model that was robust to any kind of time series dataset. It scored very well for all of the datasets and did not struggle in any of them. Also, the smaller number of features does not mean worse performance. We saw that on the previous slide, where PCA with only 10 features was better than PCA with, for example, 25. The attention model matched the performance of the other state-of-the-art methods and kept up with, for example, mutual information feature selection algorithm. Also, attention model incorporated into the model can significantly boost its performance, and because of the fact that the attention model has fully customizable architecture, it encourages further research where a lot of architectures could be researched. That will be all. Thank you for your time and have a wonderful day.